So yeah, good afternoon, everyone. Thank you for your introduction. So as you said, I'm Daniel Becker. I'm come to you today from Fraunhofer IAIS in Germany, and would like to showcase you. What is it? Oh, some of the methods and tools that we have developed in the context of assessing the trustworthiness of AI systems. So let me just tell you a little bit about it, what Fraunhofer is. Fraunhofer, for those of you who don't know it, is one of the largest research organizations in Europe with over 70 institutes scattered all over Germany, and we tackle all kinds of different research topics. But there's this research center, Berlinghofen, that is mentioned here, where there are really 3 institutes. It's close to Bonn and St. Augustine, really 3 institutes where over 800 researchers work mostly on topics in the context of AI, big data and data science, machine learning, and things like this. And there's this IAIS Institute where I come from, and there's also the group that is really targeted with the research focus on trustworthy AI systems. And in this sense, it's from the scope, what it does is really, it has a large overlap with the Confiance.ai program, in the sense that we really want to tackle these questions of what trustworthiness is in the context of AI in depth and breadth, so to speak, and also like horizontally and vertically, meaning that we also look at all the different dimensions of trustworthiness and look at what could they mean, how could they be measured in the context of AI systems, but also how could we assess certain AI systems, how could we assess companies that produce AI systems, how do they have the right processes in place, and also anything in the direction of standardization, certification of AI systems in the end. So from the high level to the low level, and today I would really want to show you something about the more lower level things that we do, which is really the tools and methods, or some of the tools and methods we have developed to make it easier, or to help really assess some of these properties that you have to check for if you want to, in the end, really get a complete picture about if an AI system is trustworthy or not. So, and also I would like to show that we do some kind of a variety of things. So these tools and methods, they are actually a little bit different, of course, and then they are also, yeah, some are more methods in the sense that they allow you to modify existing AI systems to really improve them in the respect of some trustworthiness measures, and others are actual tools in the sense of applications that try, or that should help humans to better develop these methods or these systems, and also check their properties. So the first thing that I would like to show you is uncertainty estimation with Wasserstein dropout, which is it's a tool that's actually a method to augment an existing neural network in order to, in addition to get some model outputs, also get some estimate about how certain the model is, that the output that it produces is actually adequate. So in a sense, especially in cases where the input data has a high variability, it should cover this variability in some sense, and this method is supposed to be quite simple to implement, and also useful for scalable, for large neural networks. The second tool is actually a tool which is a visual analytics tool called Trustworthy, where the idea is to harness the capabilities of humans for pattern recognition, and also to implement human intuition into the development process of an AI system by visually representing the data that you have, and also the data that the model outputs in a semantic space, in order to enable all kinds of feedback cycles to really improve aspects of the data, aspects of the model, and so on. And this is a really human-centered approach. So in the sense where the human should be in the center and really developing these things and developing intuitions and hypotheses, but many times, then you will be afraid that the human is not enough to check the system, that you should be afraid that you, in this huge search space that you have, miss some edge cases. So the third method that I would like to show you is really complementary to this visual tool, in the sense that there we use a rule-based learning approach to really systematically look for weaknesses in black box models. And the fourth one is then if you have a really like an individual instance of some model output and you really don't know what's going on there, I really would like to drill in, then we also have employ rule learning in order to generate local explanations for certain particular instances, model instances. So these uncertainty methods, there are already quite some methods that are already existing that give you, in addition to the model output, also some kind of uncertainty that the model has, how well it has identified something, or how well it has classified something, for example, in the case of model detection, object detection. And so there's also already a vanilla method available, like Monte Carlo dropout, which basically works by randomly switching off and on certain neurons and neural network. And what it means in effect, what you do is actually train an ensemble of networks instead of a single network. And this ensemble values that you get, like the mean value gives you the model output, and the variance of these outputs gives you something about the epistemic uncertainty, which means how uncertain is the model about its own, like how uncertain is the model output, and in some cases this is not enough. For example, if you look at these cases where you have to identify objects in images of traffic scenes, sometimes you could have something like a fog where it's really unclear what is actually in the image, or what is actually in front of the car, and there are lots of possibilities. So we have a high variability of possibilities here, and a really broad probability distribution. In this sense, you would like to have a system that gives you an estimate of this uncertainty. And now the idea here is, instead of just optimizing your neural network during training for minimizing some loss, you optimize it for minimizing the Wasserstein distance between the output distribution of your model and also the actual input data distribution. And in that sense, what you get is, both. You get the model output, but also an estimation of its uncertainty with regards to data variability. And we performed some benchmark tests where we compared these benchmark problems with other state-of-the-art methods, and it turns out that this method is actually competitively good, which means that it has comparative performance, and also when you measure the quality of the uncertainty estimation, in this case in terms of the expected calibration error, you're also quite good in the sense. And it also works well for data shifts. So that brings me to the second tool that I would like to show you, which is really a tool in the sense of an application. We have this kind of visual analytics tool here, which is called Scrutiny. And as I said, if you have metadata available and semantic information about your data, then it helps you to really visually represent your data in many different ways, and you can really query this. And that should help you as a developer, or should help developers to really drill into the data, look at the data. If maybe some semantic dimensions are missing, then you see, okay, if this is the case, I could go back a little bit and generate new data. Or if, for example, I see at the end that the model is somehow not performing well for some certain edge cases, maybe I can identify them and also then tune the model parameters or whatever I have, so that I should have all these kind of feedback loops. And this is a little bit how this tool looks like. So we have this surface here, then you can load in your input data, and then you have you could query this. You can type in them query strings, really query this data, and look at all kinds of distributions, or also like the scatter plot here. And then if you see that there are certain instances that are interesting or peculiar, you can also select them and really drill into these properties of these subsets, and even go down to the individual instance level, where in this case you could then, if it's in a model that works that detects something like objects on an image, then you could look also at the individual image here. So this is this is now the case if you want really to get the human in the center. But now sometimes this is not enough. So you would really like to have a way to look at your input data, for example, also to look for certain systematically for weaknesses in your input data or the model outputs that you have. And consider, like, if you really have meaningful metadata available, or you can generate it, and you can either it's already categorical in the sense, or it can be suitably discretized, then the idea here is to search for some subsets that are as large as possible, and also have an as high ratio of items within them that fulfill some search properties. For example, if I would have two attributes here like color and shape, then I would say, okay, if I look for something, then some subset like this would look like, okay, color is red and shape is circle, so that means in the sense that all these subsets are defined as conjunctions of attribute constraints. In this way, I mean, the search would output that, okay, if I look for certain search criterion, for example, something that's not well recognized as an object in my model, it could output that, okay, if the color is red and the shape is a circle, it's not very well recognized. And this is some sense, the idea here is to first of all have an automatic and exhaustive search of the whole input space, but also what you get is something that should be human interpretable. So it should also be able to, you should also be able to learn something from this, and that should help you again also, of course, to better develop your model, improve your model. And also this search covers the entire search space in the sense that it gives you all the statistically significant groups that you have in terms of the semantic dimension that you have in your data set. So now how could it look like in practice? So here's a toy example, so if you want. Here's the task was segmentation of traffic scenes, and the neural network should just reclassify each pixel within this image. And well, the task that we asked here was, can we find rules for cases where the pedestrians, for example, are not really identified properly? And what the kind of metadata that we have available here are the pedestrian bounding boxes, where we have basically just the size and the position of the bounding box, and the IOU value gives us the detection quality, meaning if I have an IOU value of 0, intersection over union, then the pedestrian is really not even a single pixel of the pedestrian is correctly classified as being a pedestrian. And now if I can search for rules that give me statistically relevant sets of pedestrian bounding boxes where this is actually the case, and I see that I get two different kinds of rules. The first one is quite easy to interpret even for non-experts, which just says that if the size of the bounding box is smaller than a certain threshold value, then the pedestrian will not be recognized, which is not surprising at all, because if there's only just a few pixels available, then at some point the model will fail to recognize this. But the second rule is a little bit more interesting, and now it needs a little bit more of interpretation, because it just says that, yeah, well, the pedestrian will not be recognized very well if the bounding box center of the bounding box position is really above some pixel value threshold. So here you need to interpret these things, and you have to develop some kind of hypotheses. And by looking at first of all, I would look at what is actually this 640 pixels, 44, what does it mean? And if you then look at the data set, you see, okay, 640 is actually the center of the image. And then you look at the images, you see that many of these images, the horizon is exactly at the center. And then you can say, okay, if this is the case, then probably many of these bounding boxes above the horizon, there are probably persons at the horizon, very far away, very small. So this is maybe, again, a reason why this model does not really recognize them. And then you can have, after you have derived this hypothesis, you can really check them. You could, for example, go back to this visual analytics tool that I showed you, look at the distributions of the bounding boxes here, and you really see that in this case, if you really filter for these bounding boxes, you see a very pronounced peak of very small bounding boxes of pedestrians that are very close to the horizon and therefore not being recognized very well. So in this sense, this kind of method gives us a kind of global explanation about weaknesses that the model has, or sometimes even something about, some insight about how the data is distributed. Maybe we think that this gives us also information about, how the data is, and we can take a look into and we can scrutinize if this is actually good? Like, is this well distributed, or is there some artifact inside that gives us a domain, leads to a domain gap if you otherwise or later on want to apply this model for real use cases? But then on the other hand, sometimes you have real cases where you want to, I think there's an image missing. Anyway, where you want to, you have individual instances where something goes wrong or something is not as you expect, and then, well, then it would be nice to have an explanation where you can really see what the model, the complex model that I know I can't understand on the global level, what it might have done or what might have affected the outcome of the model in a certain individual instance. And there's this already established LIME method, which basically has, it consists of, for the given instance that I want to explain, to generate some kind of cloud of slightly variant deviated or perturbations of these instances, and then I have this. I can fit to this cloud of instances. I fit some linear model, some model that is intrinsically interpretable. In the case of LIME, standard LIME, this is linear regression, and then the regression weights, they should give you some hint about which input, which features from the input instance that you would like to explain were important for the decision. But then in the linear expression, in some cases, they can become unstable. They can, depending on how the decision boundary looks like, it can be really that you can get very different results, even if you just a little bit change the input instance. So the idea is here to, in the second step, instead of fitting the linear regression model, we do again some rule-based rule search on this same cloud of instances in order to hopefully get all kinds of rules that are relevant in this case. So it could be multiple outputs, and that also more stable. And also, as each of these rules tell you how many of the items actually in the group that it comes out match the input search, give you some kind of hint about how good these rules actually are to explain this instance. Also, again, like a very simple example how this could look like. Actually, for a case which also works for LIME, we have here this subset of two email news groups where that are already labeled with which are Christian and atheist, and the classification task was just to really label these emails. And then the model in this case is not even a neural network; it's a random forest classifier, which is already has a very high precision, over 90%. But if you now look at the instant of certain instances, that you can see that the actual explanation is not based on the content of the email, but really on parts of the email header, which is also the result of the LIME method. But if you now look at the rules that come out by a rule-based search, you see that it really gives you the same result. So this is actually promising, but also it gives you even a little bit more, because it also tells you, if you really look into these rules, that this is actually everything that was all that this decision was based upon. There's nothing else that went into this decision. So I think this is a promising result to give you a little bit more intuition into these local explanations. And with this, I'm actually at the end of my presentation. So I showed you various tools and methods that we developed to assess certain aspects of AI systems with respect to transparency. And as I said, these are not the only activities that we are involved in. We also are involved in standardization activities and also AI assessments. And if you want to learn more about this, then there are interesting talks in the afternoon session by Christiane Fuß from DIN, and also from Bernd Eisenmann, who will show us something about AI assessments.
Yes,
Thank you
have a strong presence in the afternoon.